Introduction to Fish Scripting for FLAC2D and FLAC3D. This is Jim Hazard, Software Development Manager at Itasca. So here's the outline of the mini course. We'll start with some fish basics, variables and functions, statements, lists, and then callbacks. So for those who don't know, Fish is the built-in scripting language of FLAC3D and FLAC2D and all of the other Itasca programs. This was developed in order to give the user power to do basically whatever they want with the program. The name Fish comes from FLAC-ish, so it's the language of FLAC. Almost every data type that exists in FLAC3D and FLAC2D is also available in Fish, so you can query it or sometimes modify it. Most of them are modifiable. Sometimes the data is only read-only. You can write a Fish function with commands embedded in it, and I'll show examples of this later. You can write a command with Fish embedded in it using these square brackets, and we'll show examples of that as well. Common uses of Fish are doing parameter studies, so running multiple models and seeing what happens when you change different parameters. Customizing the physics. You can actually change the way that the physics works and call something, for example, every time step to modify something. User-defined history, so you can make a graph of whatever you want. Automate repetitive work, of course. So Fish scripting. A Fish script is just basically an ASCII file, so it's basically the same as the data files we've seen thus far. Fish is case insensitive, so if you're used to C or C++, it does not behave the same way. It doesn't matter if you use capitals or smalls. A comment is denoted by a semicolon, and you can see here in the editor, when you put comments in, they turn gray. When you create a function, you use Fish define to start a function, and you use end to end the function. Fish is functional programming, so it's not object-oriented like, say, C++. It's all about writing functions. And of course, the functions may call other functions and so on. The order in which the functions are defined does not matter. However, you can't call a function in another function if the function that you're trying to call has not yet been defined. All Fish functions and variables and so on are saved with the model state. When you give a model save command, it will store all of your Fish data as well. So the text editor looks like this. And the easiest thing here would be to just start up FLAC3D and have a look at it. I am going to use FLAC3D, so I'm going to start FLAC3D. You could just as easily use FLAC2D. Almost everything I'm doing here is applicable to both. And in cases where the files are different, I've given you in the material that you can download both the 2D version and the 3D version. So you could follow along here with 2D if you like. Also, most of the examples that I'm showing here, you can run in demo mode, so you don't necessarily need to purchase the product. So I'm just starting FLAC3D. It's appeared here on my other screen, but I've given you a project with a whole bunch of examples in it, if you've downloaded it. We will just start with a new project instead of using that one that I've already given you. So I'll make a new project. I'm going to go to wherever you have the material for this course. So in my case, I've got it in Documents, Training, FLAC3D 2024, and then there's an Intro to Fish exercises. You can see here there's a 2D project and a 3D project I've already given you. We'll just make a new one from scratch here. Let's just call it Fish 3D. So here's my FLAC3D. I'm using version 9.1, but everything I'm doing here will also work in version 9. So I start with a blank screen. Let's get writing some fish. So we need a data file. So we go new data file, and let's call it testing. You can call it .dat or .fish. A lot of people have all of their fish functions in files called .fish or .fis, just to make it clear that these are fish functions, and it can be used by multiple data files. You can also just put fish functions into a data file. It really makes no difference. So in this case, I'll just call it testing.dat, even though it will be mostly fish. I'm going to increase the size of the font here. So if I go to the controls for the editor, I can change the font size. Let's make it 16. So if you wanted to write some fish functions, as mentioned, you start with fish, define, and you give the name of some function. And I'm just copying what's in the PowerPoint if you're following along here. What you can see is that there's colored highlighting here, which is nice. I mean, you could write these fish functions in any old text editor, but if you write it within FLAC2D or FLAC3D, you get this highlighting and so on, which is nice. I'm just going to make this font a little bit bigger. Okay, so the keywords are bold purple, and then this is the name that I just made up for the function ABC. And now I'm making up a variable name called HH and give it some value. You can see that it's light purple. I can do some sort of calculation. So there's a simple fish function, what it would look like. If I run this, nothing happens because I've defined the fish function, but I haven't actually called it yet. So to call the fish function, I give the name of the fish function in square brackets like this. That will actually call the fish function. So it calls it, it actually prints to the screen the value of the function. So I made a function called ABC, and I set ABC equal to something. And so it prints out to the screen here 71, the value of the function. You can also see over here on the right-hand side, there's fish global symbols. I'll talk about global versus local in a minute, but by default, everything in fish is a global variable. So I've got a variable called HH with a value of 22, and a variable called ABC with a value of 71. This is also the name of the function. So this is what fish looks like. This is what the fish editor looks like. I've already shown you how you can change editor options. Lots of other stuff you can do, like you would expect on any editor: undo, redo. You can collapse the functions here, and I'll show later when we have loops and so on. You can collapse all the subparts of the function, which is quite nice. Obviously, you can save, open, usual stuff that you would expect from editors. You can go to a specific line. These two here are useful. What this does is allow you to add to comment a bunch of lines or uncomment a bunch of lines. So if I select everything here and I press this one, it will comment everything. And if I select everything and press the other one, it will uncomment everything. So this is just the basics of the editor. You've probably seen this before in the previous sections of the course. Writing fish functions. Obviously, you will not know how to do this, which is why you're taking this course. But what is extremely useful is the documentation. So I can go over to the help here, press this little question mark to get the documentation. Depending on what you're doing, you may want to open this in a browser rather than have it on the right-hand side. So if I press this little icon here, it will open in a browser. In my case, the default browser is Edge, but yours might be something different. So it pops up on this page here. The fish functions are described in different places. So under Itasca software guide are things that are common to all of the Itasca programs. So FLAC2D, FLAC3D, 3DEC, PFC, and so on. So under common commands in fish, you will find fish functions related to just for example, discrete fracture networks. See here, you've got fish functions related to DFN, fish functions related to, say, tables. So if we're going to table, there's fish functions related to tables and so on. Fish functions that are specific to different programs are listed under the program name. So if I go into FLAC, FLAC commands fish and workspaces, and I go to zone, there's zone fish functions, so related to faces, grid points, interfaces, and so on. So if I click on one of those, I can see all the grid point functions. And if I click on those, it gives me some more details about it. So we'll get to that in a little bit more detail later. If you really can't figure out if something is common or not common, or you just don't know how to find it, the best place to go here is this fish index. So if you go to fish index, this is all of the fish functions in all of the programs. You can search on the page. So if I was looking, for example, I wanted to know how to do sine or cosine, I can do Control F to search on the page and just hit sine. And there we go, math.asine, math.sine, math.sinH, and so on. This is how to find all the individual functions. If you just want to learn about writing fish in general, you go to this scripting section here. And there's a fish scripting reference, and you can just read through that. And a lot of what's in here is what I'm telling you right now. So you can take this course, and you'll probably know what you need to know about fish, but you can go here for a refresher about some of the details and so on. Especially helpful is this fish tutorial, which just walks you through the basics of using fish. Okay, so that is the help. Now let's go back to our FLAC3D. So here's my little function. We've already seen this. Because this is a programming course, you always have to start with writing hello world. So fish function to do that might look like this: fish define hello. And if you want to write to the console down here, you do this. You go io.out. IO stands for input output, and then out means obviously I'm outputting. And then I put a string, and strings have to be in quotes. It can be a single quote or a double quote, it doesn't matter. And I just say hello world. And that's the whole function. And if I say hello in squared brackets, it's going to call the function. So if I run this, you'll see it printed to the console down here, hello world, as I told it to. This io.out is quite useful, especially when you're debugging. There isn't a built-in debugger like there is in, say, Visual Studio. You can go through here and add these print statements at different places in your fish function to try and figure out what's going on. And this is extremely useful. And again, if I click on the little fish over here, I can see this list of global fish symbols. I've got the ABC still, the HH still, and now I've got another one called hello, which is just a function. By default, returning 0, because I didn't actually return anything. I didn't set hello equal to anything. Okay, let's go back to the PowerPoint for a second. Variables and functions. So you've just seen me declare variables inside of a function. I can declare variables. I don't even have to say fish define and fish end. If I'm being lazy, I can just define a variable inside of square brackets like this. And this is very common, especially when you're trying to define parameters. So here's an example where maybe you want to list at the top of the file some of your material properties. So I would give a fish variable called bulk equal to 1E9 and a fish variable called shear equal to 0.7E9. And then down here in the commands where I specify the bulk modulus and shear modulus, I just give the fish variable name instead, and I put it in square brackets. So this is pretty useful because imagine this bulk modulus and shear modulus might be used at multiple places in the data file. If I always just refer to the fish variable, I can change it once at the top, and it will change it everywhere down below. So this is a super useful way for doing parameter studies and things like that. So that was just showing you how you can put a fish variable inside of a command. You can also put a command inside of a fish function. So here's, for example, a fish function that will set the Young's modulus on zones. And so you can do that with the command. You've seen this before, block zone property Young. You give some Young's modulus, which could be a fish variable. But here what we're doing is setting a different Young's modulus for all the zones. For every individual zone has a different Young's modulus according to its depth. So you calculate the depth, you calculate the Young's modulus, you get the zone ID, and you give this command to change the Young's modulus. This is a dumb way to do it. You wouldn't actually specify a command for every single zone. You can just use a fish function to specify the zone Young's modulus. But this is just an example to show you how you can embed a command within a fish function. Data types and variables. Variable types do not need to be declared. So unlike C or C++, the fish program tries to figure out what the type is based on what value you assign to it. So if I say A equals 1, it's an integer. If I say A equals 1.0, it's a floating point number. If I say A equals quote 1.0 quote, it's a string. These things can actually change as you go along. So actually, maybe the easiest thing here would be to just show quickly some examples. So if I go back to my FLAC3D, I can delete this stuff. Maybe I want to put model new at the top, so I'm not carrying around all this other fish every time I run this file. So I say model new. Let's do what I just said. So here I say A equals 1. If I run this, it tells me over here there's a global symbol called A with a value of 1. It's an integer. I then add another line below here, A equals 1.0. A has now got a value of 1, but it's a floating point number. Right? So it started out as being an integer, and you changed it to a floating point number, and that's perfectly fine. And you can actually force it to be one way or the other. So maybe I want, for whatever reason, I want that 1 to be a floating point number. I can say A equals float 1. By default, if you just put 1, it will think it's an integer. But if I force it to be a float, it will turn it into a float. So this is sometimes useful in, for example, when you're doing division, you might want to do something like this. Result equals float 5 divided by 2. Because if you just say 5 divided by 2, these are both integers, so it returns an integer, which is probably not what you want. And that result is 2.5. So the variable types are intuitive. You have floats, you have integers, you have strings, as I mentioned. So I could say something like test equals my string. Right, so now I've got a string type. These are the basic types. We have more advanced types. There are vectors, there are tensors, there are matrices. The tensors and matrices may be less commonly used, or at least until you start getting into stresses and strains for the tensors. But vectors are super useful and very commonly used. For anything to do with like displacements or positions, you can use vectors. So the syntax for vectors looks something like this. Let's just make a function. Let's delete this stuff. Fine. Test vector. So a 3D vector would be something like this. A equals vector, and you give 3 values, 1, 2.1, 3. Even in 3D, you could make a 2D vector. So you could say something like this, A2D equals, vector. Notice how when I made a typo there, it doesn't turn bold. So I've known that I messed something up. When I actually type vector, it turns bold. So A2D might just be 1, 2.1. If I run this, That's actually incorrect. It says A is an integer and A2D is an integer. They're not actually, they're vectors. I can double check that. I can say io.out A, io.out A2D. It will print the values to the screen. Oh, I need to call a function. Oh, that's why it says they're integers, because I defined the function, but I didn't call it. So let's call it test vector. There we go. Right, so now it's giving me the right solution here. It's telling me what A is, what its value is, and it's a vector 3, and A2D and its value is vector 2. And also when I say io.out, it prints them to the screen as well. Once I have vectors, I can get the components, which is often very useful. So something like C equals A2, that will give me the Y component. So that should return 2.1. Say D, and if I don't like using the component as a number, I can just use X, Y, Z. So I can say D equals A arrow. So I put a minus sign and a greater than sign, which is an arrow. Y. So this will return the Y component. So if I run this, C should equal 2.1 and D should equal 2.1. These do the same thing. Once you have a vector, you can also do operations on it. So for example, E equals A times 2. I'm just multiplying every component of the vector by 2, and I can do divide and other things. Also extremely useful, I can get the magnitude of the vector, which is just square root of A squared plus B squared plus C squared. So I can say F equals math.mag of E. So I run that. Right, so here A is 1, 2.1, and 3. E is A times 2. So E is 2, 4.2, and 6. F is the magnitude of that vector, which is 7.5921. So there's other useful functions. I can go back to the PowerPoint here for a second. I showed you math.mag. You can have math.cross to get the cross product, math.dot, math.unit, and so on. So the vectors are extremely useful. Okay, let's talk a little bit about global versus local. So like I said, if I just declare a variable and I assign it some value, it's a global value, and it will appear in other functions. So let's make this a little bit simpler here. Fish define test global. A equals 5. I run this function. So here's my function. I've defined a global variable called A. By default, it's global. It's equal to 5 over here. So let's pretend I have another function, fish def test global 2. B equals A times 2. This will work. It knows what A is equal to. It knows that A is equal to 5. It's a global variable, even though it was defined in this function. All functions know about A. So I can do this. B equals A times 2, and B should then be equal to 10. So if I run this whole thing, there, A is 5, B is 10, everything works. Now, sometimes you might not want those things to be global. You might want to have variables that only exist within a given function. And this is a good programming practice. And if you've programmed in other languages, you will know that this is a common thing that people do. And if you just want it to be a variable that exists within a given function, you just give the keyword local. So here I would say local A equals 5. This value of A exists in this function, so let's do something like this. Junk equals A times 2. This will work. When I get down to the next function, and I say b equals a times 2, this will not work because a only exists in this function. It is not global. So it should throw up some sort of error here. Yeah, unrecognized word, you cannot create a new symbol, blah, blah, blah. It's telling me that it doesn't know what a is because it's local to this function. So a is 5. Oh, a, it doesn't even appear over here, right? So now because a is local, you don't see it here in the list of symbols. You just see junk is 10, and we can't use a in the next function. So this is sometimes useful just to make your coding a little bit cleaner. You certainly don't have to do this, but you will see this in some of the examples. Okay, that's pretty much all I'm going to say about variables and functions. Obviously, a big part of doing fish is doing some sort of math or some sort of calculations. These symbols should be pretty familiar to you. Divided by, times, minus, plus, this little hat is raised to the power of. Then we have a bunch of built-in functions, as I briefly showed in the help section. Math.tan, math.cos, math.sine. So all of trigonometry, pi, random number generators, which are useful, square roots, so on and so on, absolute value. There's many more. This is a lot of the useful ones. So this is all general stuff about writing fish functions. We haven't talked anything specific to FLAC3D or FLAC2D. As I showed in the help earlier, you can drill down into the help and look at the fish functions associated with FLAC2D and FLAC3D. And again, almost all data that exists for FLAC is accessible with fish. So for example, grid point positions, grid point displacements, velocities, zone stresses, zone strains, zone properties, so on and so on. So pretty much everything that exists in FLAC3D you can access with fish, and a lot of them are modifiable. So for example, I can change the properties. I can change the displacement. Some of them are not modifiable. I can't, for example, change the position of a zone. The position of a zone depends on the position of the surrounding grid points, so I can't just go and change it. Okay, so now that we've seen data types and variables and functions, almost always what you want to do is use fish statements to do something. So often you're looping through and doing a calculation. You might need if statements and end if statements for conditionals. All of these things are available to you. I won't necessarily go into detail about all of them, but certainly the if statements and the loops are something that you will almost certainly use if you're using fish. So the if statements look like this. If you've used any other programming, you will be familiar with if statements. So I have a fish function. I can check something. If xx is greater than 0, then do something, else do something else, end if. This is the syntax. You say if, you say else, you say end if. There's also an else if you want to have multiple conditions here. See here how it's indented. You don't have to indent it. It's not like Python where the indentation is mandatory. However, it makes it a little bit easier to read if you indent things inside of these ifs and else ifs, and also inside of these fish functions. Again, not mandatory, but helpful. The comparison operators should almost be all familiar to you. Equals, greater than, less than, greater than or equal to, less than or equal to. The only one that might be a little bit unusual is this hash symbol, which means not equal to. In other programming languages, they sometimes use like a exclamation part, equals. In fish, we just use a hash. That's what if statements look like. The second most useful thing that you will probably use is loops. So let's pretend for some reason you wanted to sum the numbers from 1 to 10. You can do that with a loop. So here's a fish function, fish define. You know what? It'll be easier just to show it in the program rather than looking at this PowerPoint. So fish define sum end. All right. So I'm going to loop over all the numbers from 1 to 10. So I do something like this. Loop I 1 to 10. That's the syntax for looping over numbers from 1 to 10. Each time through the loop, this variable I will assume this number. So the first time through I is 1, the second time through I is 2, the third time through I is 3, and so on. I do something inside the loop, and then I say end loop. I can also use end loop without an underscore. It doesn't matter. Either one is valid. Just to show you that that works, I'll change it to end loop. There, it turns both. Same with if statements. I could say end underscore if or just end if. Right, so I want to sum something up here, but I need a variable to sum. So let's say we'll start with s equals 0. And here I can say s equals s plus 1. And that's the end. So it's going to loop through this thing 10 times, and each time it's going to add 1 to s. And at the end, I should have whatever the sum of the numbers between 1 and 10 is. So I call the function by putting it in square brackets, and I run it. Oh, and for some reason that didn't work because, oh, what I did here was I did s equals s plus 1. So it's just 1 plus 2 plus 3 plus 4 plus 5 plus 0. What I wanted to do was s equals x plus I to add up the numbers between 1 and 10. So let's do that. Right, so now I have 55. So 1 plus 2 plus 3 plus 4 plus 5, and so on, adds up to 55. And you can see at the end of the loop, I is 11, because it goes from 1 to 10, and then it turns to 11 and drops out of the loop. So this is just demonstrating how a loop works. I is from 1 to 10, and I can use I inside of the loop to do a calculation. I can make this a little more general. Instead of always looping from 1 to 10, I can have an input. So let's say the user inputs a value that they want to sum, some sort of input variable of n. And so here, instead of saying loop I from 1 to 10, I can say loop I is from 1 to n. And I'll get the sum of the numbers, whatever the user defines. So here, when you call the function, you have to specify the input in the brackets. So let's make it 20 instead of 10. Let's see what I get. So now it sums the numbers from 1 to 20, and the answer is 210. One other neat thing, this is the old-fashioned way of doing it. You can actually do it in a slightly more modern way by saying something like this: s plus equals 1. Sorry, s plus equals I. This is familiar syntax if you're using C or C++ or something like that. So this will do exactly the same thing. It's just a little bit more concise. I still get 210. Now let's pretend you wanted this function to return a value. There's two ways to do that. I can set the name of the function equal to the return value. So at the end here, I can just say sum equals s. And down here, I can say something like IO equals out sum 20. So it's going to call a function, it's going to return the value, and it's going to print it to the screen. All right, so here it's printing out 210. So that's one way to do a return. This is slightly confusing, setting the name of the function equal to the return value. You could just do this instead. You can just say return s. I think this works. Let's see. Yeah, so this does the same thing. This is a little bit more common syntax if you're used to other programming languages. You just return the value, and then when you call the function, the value that is returned is given here. So that's a basic, like a for loop, you would call it in C. There are other ways to control the loop. So you can exit out of the loop, or you can bypass the rest of the functions, sorry, the rest of the statements inside a loop. So just, I'll show you what that looks like. So this also shows you how we use an if statement. So let's pretend I only wanted to sum up to the first 5 numbers, regardless of what the user input here. So I could say something like this: if I is greater than 5, exit loop end if. So what's going to happen here is the first time through, it's going to add up to s, add to s, add to s, add to s. If I is greater than 5, it's going to drop out of the loop and just return a value. And so now I should just get the sum. Even though I told it I wanted 20, it's really only going to give me the first 5. And that turns out to be 15. So this exits the loop completely and returns s. The other thing you could do is maybe there's certain things that you just, certain conditions where you just want to skip this addition here. So I could say, for example, if I equals 5, I don't exit the loop, I just say continue. What will happen is it will skip the rest of the loop, but it will keep on and go to I equals 6, and I equals 7, and I equals 8. So only the case of I equals 5 will be skipped. And so now, instead of getting 210, which was the sum of the first 20 numbers, I should get 205 because it's skipping I equals 5. And there we go, that worked. So these are useful constructs to control the loop, either skip to the next one or drop out of it completely. Okay, in the PowerPoint here, I've got an exercise for the user. Sum all numbers from I to 100 except for 50. We've basically just done it here already. This is exactly how you could do it. So you don't necessarily have to do this exercise. Okay, next topic is lists. Let's just go back to the PowerPoint. So lists are basically just arrays. In the old days of Itasca software, we used to just have arrays, and these were a little bit uncomfortable. You had to specify the size of the arrays in advance, and you don't always necessarily know the size of the array in advance, and there were other problems with them. The arrays still exist in FLAC and FLAC3D. You can still use them, but 99% of the time you'll just be using lists. It's just a more flexible, more usable type of array. So this is what it looks like. You can make a variable and set it equal to a list. This will just be an empty array, okay? Then you can start appending to this list. So again, you don't have to pre-specify the size. You can just append to the end of it. So I say my list bracket end equals something. And each time through this loop, it's just going to stick a number on the end of this list. The cool thing about lists is that it's super easy to loop through them. So I haven't shown you this yet, but this is another way of doing a loop. You can say loop for each item. This is a user-defined variable. And this is my list that I declared up here. And so what this will do, this is like what you see in Python. It will loop through every item of the list, and then you can do something with those items. So here I'm just printing them to the screen. If I say, or if I show the list in the list of global variables, it won't tell you what's inside of it because it could theoretically be 100 or 1,000 or 10,000 things. And we don't necessarily want to list all of those on the screen. You can force it to list what's inside by using this fish list contents, and you give the name of the list. So before I move away from this, the other cool thing about lists is we have these built-in functions. So it's easy to get the minimum value in a list or the maximum value in a list, or the size of the list, or you can sort the list or the sum of the list, and so on and so on. So all these things are totally useful. So let's just demonstrate here. We'll just show you what's in the PowerPoint, but we'll just walk through it so you can see how it works. Fish define make list. So what I had was my list equals list. This is an empty list. Loop I 1 to 10. My list end equals I times 1.5 or whatever you want, and loop. And then what I did was I looped through all the items in the list. Loop for each item, this could be anything, my list, io.out item, and loop, and make list. Okay, so if I run this, you can see over here I've got a fish symbol called make list. Sorry, that's the function. I've got a fish symbol called my list, which is a list of size 10. It doesn't give you the values. It just tells you that it's size 10. If I want the values, I need to print them out inside of a loop like this, so you can see it printed to the screen. Or I can give a command like this, fish list contents. You have to give this keyword contents, and then it will dump out everything that's inside of my list. And it tells you what type they are as well. The list can be full of any type. They don't have to be floating point numbers. They could be integers. They could even be vectors. They could be other lists. You can do all kinds of crazy things with these things. They don't even necessarily all have to be the same type. So fish, my list 1 could be a string, and my list 2 could be a float number, and so on. Most people don't do that, but it's certainly possible. The way to access the individual items in the list, if you're not looping through like this, maybe you just want to get list number 3, you can say io.out my list 3, and that will output the third item in the list. Note that lists in FLAC3D and FLAC2D start from 1, right? So the first entry in the list is my list 1. It's not 0 like it would be in C. So this is how you can access the individual items. So another way, if you don't, for whatever reason, if you didn't want to use loop for each item my list, you could do something like this: loop I 1 to list.size my list io.out my list I. Right, that will do exactly the same thing as up above. So now it's printed out the values here and printed out the values again, and then printed out the values again because I fished list contents at the end. So this is how you use lists. And again, there are all kinds of useful functions here. You could say sum equals list.sum my list. This will automatically sum up all the values in the list. Here you can see 82.5. The reason that lists are important, it's not just because you might want to create your own lists, but because all of the data in FLAC2D and FLAC3D are stored in lists, almost all of the data. So all of the zones are stored in a list of zones. All of the grid points are stored in a list of grid points. All the structural elements are stored in a list of structural elements, and so on. And so very commonly you will, for example, loop through all of the zones and do something. And the construct would look like this: loop for each. This local is optional. Here I'm just telling it, I'm making a variable called ZP. In this case, it only exists within the function, but you could make it global, it doesn't matter. Loop for each local ZP zone.list. So I'm looping through all the zones in the zone list. And each time through the loop, this variable ZP is pointing out one of the zones, and I can do something with it. Same construct for grid points, same construct for structural elements. So we have some examples. I'll show this in an example in a minute. We just need to talk about one more thing before we get to the example. As well as all the data that exists in FLAC2D and FLAC3D, so stresses for zones and displacements for grid points and so on, you can create your own data for these things. And this is what we call extra variables. So every zone, every grid point, every structural element has up to 128 extra variables. So you can put whatever data you want in there. And again, it can be integers, it can be strings, it can be vectors, it could be anything. This is useful for doing your own calculations and storing information. It's also useful because you can plot it. So I can actually store something in an extra variable, and if it's a number, like a integer or a float, I can plot it. Obviously, if it's a string, it's not that easy. The syntax looks like this. So I can set an extra variable. So here I'm looping through all the zones in the zone list. I can set the zone extra variable for this particular zone. And I say, comma 1, this is the first extra variable. Remember, I could have up to 128 extra variables. So I'm setting the first extra variable equal to the Young's modulus times some random number. I could set the second extra variable, zone.extra zp comma 2 equals to something else, and so on. Okay, so we have an exercise here. Instead of making you type all this in, we can actually just open the exercise that I've given you. So let's go back to our project. I can say open. This is exercise 5. So you can see here, I'm making a brick size 3 with 3 by 3 by 3 zones. So it's a 27 zone brick. There's the 2D version commented out here. If you're running this in 2D, you can just uncomment this and run it instead. And this is just a 3 by 3 brick. I'm assigning it elastic. What I'm going to do here is use this math.random.uniform function. This generates a random number between 0 and 1. Every time I run this, I'm potentially getting different random numbers. If I want it to be consistent so that every time I run it, I get the same sequence of random numbers, I can specify a random seed here. So I say model random, some number close to 10,000. And then every time I run this file, I'll get the same sequence of random numbers. If I don't specify this, I'll just get a different sequence of random numbers every time. So just so that you following along at home will see the same thing that I'm seeing, we can specify this random seed. Then we create a function. We're going to loop through all the zones. So for each ADR, that's just short for address, I'm setting the first zone extra variable equal to a random number. And this is a random number between 0 and 1. If you're not sure what this does, you can just click on it and hit F1, and it'll bring up the section of the help file related to this fish function. So it's telling me right here, math.random.uniform, get a uniform random number that falls in a range from 0 to 1. If I give a number inside of the brackets here, it actually returns a list of random numbers with a size equal to that number. We don't want to do that in this case. So we can just run this. Plot it to make sure it works. So let's go up here and make a new plot. We can plot zones. So here's my 3 by 3 by 3 zone model that I just created. Now, I can change the color by to contour. And for value, I can change it to extra for extra variable. And it defaults to the grid point extra variable. But in this case, we set the zone extra variable. So we can change the source to zone. And now I can see these zones have different values. They're just random numbers between 0 and 1. The red contours are close to 1, and the blue contours are close to 0. So you can see how that works. And just for fun, you could change this random number seed and run it again, and you should see something a little bit different. So that's just a super simple example of how you can loop through zones, how you can use the zone pointer to do something. In this case, set extra variables, which are potentially super useful. Here's another exercise. Let's look at this one. Again, you don't have to type it all in. Let's just open exercise 7. There's a 2D version of this too. It was different enough that I made a separate data file for 2D. I'll just show the 3D version, but you could follow along in 2D if you like. What we're doing here, this is a little bit more complicated. We're using fish as a history. So you've seen already, you can make a zone history of displacement or stress or whatever you want. Maybe you want to create your own variable or your own value of something and take a history of that. So you can plot a graph of it. So what we're doing here is we're just making a simple 1x1x2 brick, and we're subjecting it to like a UCS test. So let's just run lines 3 to 8 here. So it creates the brick, it makes it a more Coulomb material, it gives it properties. It's preventing displacement on the bottom. So position Z0, we're fixing the velocity. And on the top, we're applying a negative velocity. So essentially, we're squeezing this thing. So we can look at it. Let's go back to our plot. This little square with the circle in the middle to reset the plot view, or you can also hit Control-R, it does the same thing. So here I've got just 2 zones on top of each other. And again, I'm fixing the bottom and pushing down on the top. Let's pretend we wanted to record the total load being applied. So I'm applying a velocity, but what I really want is the total force being applied, or maybe even the total stress. In this case, it's going to give you the force. And so what it does is it adds up the unbalanced force of the 4 grid points on the top. So I have a fish function called load. To get the 4 grid points on the top, I first need to figure out their addresses or their pointers. So I say AD1 is the grid point nearest to 002, and AD2 is the grid point nearest to 102, and so on. So I've got 4 grid points on the top at these 4 coordinates. We have global variable names, AD1, AD2, AD3, AD4, which correspond to the 4 grid points. Now the fish function load just takes the unbalanced force, the Z component of the unbalanced force, and adds them up. And then I can take a history of that. And so by default, a history is taken every 10 steps. So every 10 steps, it's going to run this fish function, do the calculation, and return this value of load and store it in the history. And then I can just plot it. I take another history of displacement, I turn off large strain, I cycle 1,000 steps. So it's going to call this load function 100 times. So I can run the whole thing. And this is the syntax for recording a fish history. If I've defined a fish function, I need to say fish history, and then I just give the name of the function. I don't have to put it in square brackets. I already said here that it's a fish history. I don't need to tell it that it's a fish function. It's smart enough to figure that out. So I run this. Let's make a new plot. And we'll plot a history chart. So here's my fish function called load. I can add this. So you can see here, it's showing me the calculated load versus step. If I change this history series to show me lines and marks, oh, I wanted to say both, right? So I can see here it's taken 100 fish queries. It's calculated that load 100 times, and it's recorded that as a history. So a couple other things to mention here. Notice the unbalanced force at each grid point is actually a vector. So if I want to get the Z component, I can do this, unval.z. Another way to do it would be to get the unbalanced force vector and just get the Z component by using the arrow like this. We saw that before. So you could do something like this. That should also work. It's the same answer. Anyway, there you go. So this is a relatively simple example of how you can create a fish history. Okay, that's the real basics of fish. I mean, you've seen loops, you've seen if statements, you've seen how to access data, you've seen extra variables, you've seen fish histories. Now we get into stuff that's slightly more complicated. If you haven't used FLAC or FLAC3D in a long time, you will have not seen anything like this before. This was new in version 7. And what this is the ability to use multi-threaded fish. So often people have very big models and they want to use fish on them, and the fish functions can be quite slow. You can do multi-threaded fish using splitting and operators. So let's have a look at that. So splitting, you can send a whole list as input to a function, and it will intelligently split the calculation amongst the different processors on your computer. This is obviously faster because it's doing it multi-threaded. It also is a nice syntax because you don't actually have to write a loop. You just send the whole list, and it will intelligently split it up and do the calculation. So here's a relatively simple example. I create a model. I create a brick. By default, if I just say zone create brick, it's a 10 by 10 by 10 brick. So it's got 1,000 zones in it. I group all the zones between 0 and 5. So the bottom half of this thing, I give them the group name bottom. Here's an example of how I can make a list of the x coordinates of all grid points. So I just say global. I don't have to say global. Again, by default, it is global. I can just say x list equals the grid point position. And normally you would just give a single grid point, and it would return the grid point position of the single grid point. In this case, I'm sending the whole list of grid points. So I say the syntax looks like this: : gp.list. I'm sending the whole list of grid points to this position function, and I'm getting the x coordinate, and I'm returning that and putting it into another list. So what this does is it gives me a list of floating point numbers, and these are the x coordinates of every grid point in the whole model. And it does this in one shot. I don't need to write a loop. I just send it the whole list to the function. You can do the same sort of thing by using a fish operator. So here's an example where I set the pore pressures on all the grid points. Say fish define set pp and make a loop. You know what? It'll be easier if I just show this in the code. So let's make a new data file here. Let's call it splitting. I'm going to copy what's in the PowerPoint. Model new, zone create brick, zone group bottom z05. Okay, so the first function was just making a list of the x coordinates of all the grid points. So this is what we call splitting. You can do it all in one line. You don't even need a define and an end define or whatever. gp.pause, and here I send it the whole list using this 2: syntax. gp.list. If I just do that, it will actually fill up the list with vectors of positions. So let's just do this for fun and see what we get. So I've got a list of size 1,331, which contains the position of all the grid points in here. So I could say fish list contents x list. Right, and so it prints to the screen. I've got 1,331 vectors here stored in this list. The example in the PowerPoint actually just took the x coordinates, so I can just add this. And if I do that, I just get the x coordinates instead of, now they're just floating point numbers. So now I've got this big list with all of the positions of all of the grid points, and I could use that for something else. Second example is I can use splitting to make a list of all the zones in a given group. This is also a very common thing that people do. So it might look like this. Bottom zones equal zone.list zone.isGroup. So this is a function that returns true or false, depending on whether or not the zone is in the group. And so what I have to do is send it, well, you know what? Let's do this without splitting, and then we'll do it with splitting, just so you can see what I'm doing here. Fish define group make group list. I could say something like this. For each that P in the zone list, if zone.isGroup ZP, so that's the pointer to the zone, and then I have to give the group name that I'm looking for, so bottom. So if zone is in group is true. Oh, I need to make a list first, right? So I say bottom zones equal list. That's an empty list. And remember, I can just append to it. So I can say bottom zones end equals ZP. So it's going to store all of the zones that have the group name bottom in a list called bottom zones. And if and loop and again, I can say fish list contents bottom zones. Let's get rid of this so I don't have too much being written to the screen. And we're not here yet, so let's just comment that out. So I run this fish list contents bottom zones type. Oh, I forgot to call the function again. So obviously I need to call the function make group list. All right, here we go. So remember, the zone create brick is a 10 by 10 by 10 group of zones. I can even just go look at it here. I can change the label to group, right? So it's 10 by 10 by 10. The top half is just called brick 1, and the bottom half is called, the group name is bottom. So 5,000 of these zones have the group name bottom. I go back to my example. I loop through all the zones, and if the zone is in the group bottom, it added to the list. If I printed out the list, I've got 500 zones. These are the zone IDs here. So this is 1, 2, 3, 4, 5, 6, 7, 8, 9 lines to do this, and also is single-threaded. I can do the same thing in a multi-threaded way in one line, like this. So I say bottom zones. Again, this is the list that's going to create. Zone.list, zone.isGroup. This time, instead of sending it an individual zone, I can send it all of the zones. So I say : zone.list. And again, I give the group name, bottom. That's it. This is straightforward, zone.isGroup. Send it the whole list and the group name. But recall that zone.isGroup returns a true or a false. And so that's why you need this extra little bit here. I say zone.list, zone.isGroup, so that it turns that true or false into a list of zones rather than a list of Booleans. So now I can do the same thing here. Let's see if I got the same thing. So it did exactly the same thing. It's just that now I did it in one line and I did it multi-threaded, which is cool. Sometimes you can't do this splitting in one line. Some of this syntax gets a little bit confusing, and sometimes it's just not possible. What you can do then is create your own fish function and send it a whole list of things, and it will run that fish function in a multi-threaded way. And it's basically exactly the same as fish define, except you say fish operator. And instead of having a loop inside of it, you just get rid of the loop and you take as an input the zone pointer. So I'll just give an example. So let's pretend we want to set all of the pore pressures on grid points. So this would be, so let's show it 2 ways here. Single threaded way. Fish define set TP loop for each TP gp.list. And I say GP port pressure equals some calculation, whatever, 10 minus the port pressure depends on the position. So GP dot pause, sorry, depends on the vertical position. So GP dot pause Z coordinate times gravity times water density. And loop and set PP. So here you could run this to set the port pressure on every grid point according to some calculation. I can go and look at my plot. I can contour by port pressure. Right, so it's setting the port pressure based on the Z coordinate. It did this in a single threaded way, and it took me 1, 2, 3, 4, 5, 6 lines to do it. If I want to do the same thing in a multi-threaded way, it's super easy. You take the same thing, you just change the define to operator. You get rid of this loop, and the input to the function is GP. And then when you call the function, you send it the whole list. So again, I say it's colon, GP.list. So what it does is I send the whole list, and it splits it up intelligently onto multiple processors and executes this function on multiple grid points simultaneously. So this will do exactly the same thing as here. It will just do it in a multi-threaded way. So just to make sure that works, let's comment this out on the whole file from the beginning. Have a look at our plot and see that we got the same thing. So in little models like this, it's not really that useful. You know, single-threaded, multi-threaded, it doesn't make that much difference. If you have a really big model, it starts to make a difference. And where it really makes a difference is if you are doing it every cycle. So there's some more splitting exercises included with the examples that I've given you. We'll skip over those. This gives you the basic idea of how it works. Oh, one thing I should mention here is that sometimes you may need to mess with a global variable. So you can specify as many local variables as you want inside of an operator, right? I can say, you know, local test equals GP pause GP D times 100. That's all fine. That will work. And let's get rid of all this stuff now that we're messing with operators. So it's happy to deal with local variables because they only exist inside of the function. But if I have a global variable, it won't work. Because what's happening is this function is being executed simultaneously on multiple different processors, and it doesn't know how to add up to a global variable, right? So this should probably throw some sort of error. Yeah. And normally, if you have some sort of global variable, what you're doing is adding to it. You're accumulating something. So you might want to do something like this. Global, here I would say test. Let's do this, global test equals 0. And then here I would say something like test plus equals something. I can't do that in a multi-threaded way. It doesn't know how to add up to the global operator, sorry, the global variable. However, it is possible to do that. And what you can do is you use what's called a lock. So if I put lock on here, oops. What this means is that when it's going to add something to test, it freezes all of the other processors and adds to the test. And then when one of the other processors get to the point where it's going to add something to test, it freezes all of the other processors and adds to the test. So then these things aren't writing at the same time to the same variable. So if I do this, it will work, hopefully. Yep. So if you need to do something with a global variable, you can use a lock. Otherwise, local variables and things like this will work. Okay, so last topic. Like I said, these operators are most useful if you are calling something every step. And the way to call something every step is with something called a callback. So what is the callback? Fish functions may be called every calculation cycle. And this is often useful if you're messing with the physics. This will definitely slow down the execution. So imagine you call a function every cycle that loops through all the zones and does something. This will certainly slow down the calculation. It is possible to also use callbacks to call a function not necessarily every cycle, but you could call, say, every 10 cycles or every 100 cycles. That will make it go way faster if you can get away with it. Of course, the other thing that will make it go faster is by using these operators that we just talked about, because it will run your function in a multi-threaded way. So the syntax looks like this. You say fish callback add. You give the name of the fish function that's being called every cycle. You give a number. The number tells you where in the cycle sequence it's being called. This is the cycle sequence for FLAC3D and FLAC2D. This is way more detailed than you probably need. And unless you're a super advanced user, you are not messing with this calculation cycle. So most of the time, you just want to call something every cycle. It's not really important where it lands in terms of the calculation cycle. So you just specify a value that's maybe less than 0 or slightly greater than 0. So somewhere around the start of the calculation cycle, you will call this function. So at a minimum, fish callback add the name of a fish function and then some number, which could be 0.1 or minus 0.1 or something like that. You can add keywords here. So a very useful one is, for example, interval n. And what that means is instead of calling it every cycle, we'll only call it every n cycles. And that will make things go faster. So for example, fish callback add something, 0.1 interval 10. We'll only call the fish function every 10 cycles. You can also specify which process. So if you're running a coupled analysis, maybe you only want to call this function during the fluid steps. You can force it to do that. So just to finish off here, we'll show you kind of a real world example of how this is useful and how you might use it. This was an example of some sort of borehole or something like that, where they were injecting something cold into it, and it was causing the ground to freeze. So you've got some sort of saturated material here at some background temperature, in this case 50 degrees. We're applying some sort of very cold boundary condition here on the corner, and this is causing this saturated ground to freeze. And what happens then is when the ground freezes, it changes its stiffness, becomes more stiff. And so what we wanted to do was look at the temperature changes and use that to change the properties of the material if the temperature dropped below 0. This is all in Celsius. So you don't have to type all this out. We can just have a look at it. So if you go to your example and you open exercise 11, again, there's a 3D version and a 2D version. I'll look at the 3D version. So here we're creating this cylinder that I just showed you. We're grouping everything and calling it unfrozen. We're specifying its elastic material. We're specifying some properties. These are the unfrozen properties. We're specifying the boundary conditions. This is a thermal example. So we say model config thermal. We give some thermal properties. We set the initial temperature to 50 degrees. And then we fix the very bottom left corner to a temperature of minus 200 degrees. What's going to happen is that cold front will move through the system here through time. So we solve for some amount of time. Now, here's the fun part. As this is progressing and the temperatures are changing, we want to freeze the ground and change the properties. And And so you could write a fish function and call that every cycle, but we can do it faster by using this fish operator. It's exactly the same as a regular fish function, just without the loop in it. So instead of having a loop, we send it a zone variable. And then we do a bunch of calculations. So there's an expansion that depends on the porosity. We get the bulk module. These are local. Remember, we can put local variables inside of an operator and everything works. So we have the expansion for this zone, the bulk modulus for this zone, a stress increment, the bulk modulus increment, so here we're changing the bulk modulus if it gets frozen. And here we're also changing the stress if it gets frozen. So it becomes more compressive. And then we change the group name and call it frozen. So this is one operator. And then the second operator is here. It checks if this group is already frozen. If the group is already frozen, it doesn't need to do anything. We can skip this. So it just returns 0. If the temperature is greater than 0, we don't need to do anything. It just returns 0. So if we get to here, it means that it's not already frozen. The temperature is less than 0. I'm going to call this function, which is going to change the bulk modulus and also change the stress because the ground just became frozen. So I solve a couple thermal mechanical analysis over to some amount of time. And then I say fish call. And remember, I have to give a number. This is where it is in the cycle sequence. It kind of doesn't really matter what this number is. And then I give the name of the fish function in square brackets, so ground freezing. And I send it the whole zone list because as an operator, I need to send it the whole zone list. An operator can call another operator, and that's what will happen here. An operator cannot call a regular fish function. It doesn't know how to do this splitting and multi-threading. So here I'm calling an operator by sending it the whole zone list. And here it's calling another operator and sending it the whole zone list. So we can just run this thing. And this is the kind of example where these operators are useful because you're doing something on all of the zones, potentially every cycle. It turns out to be not every cycle in this case because it skips the ones that are already frozen and so on. But you can imagine how this could be useful. So let's go back to a plot here. If I plot by group name, I have to zoom in here. All right, let's change the color scheme. Let's make frozen blue. That makes sense to me. All right, so the frozen zones are blue. The not frozen zones are pink. They're theoretically changing as this goes along. We can, instead of plotting the groups, we can show the temperatures. All right, so you can see the temperature in this bottom corner is close to -200. Temperature in the background was 50. And so anything that's below 0, which is basically the boundary between these two orangey colors, something that's becoming frozen. So I can go back to my label. See, now the frozen region is getting bigger here as this cold front is propagating out. Here's just an example of how you can use fish calls so that something gets executed every step, and also how you can use operators to make that go faster. Okay, that is the end of the introduction to fish. There are other topics that I didn't talk about. File reading and writing is useful information. Tables are useful things, geometries, scalars, vectors, tensors. There's lots of things related to fish that I didn't talk about. You are invited to go and explore that on your own time. All right, thank you for joining.